A motorboat heads upstream on a river where the speed of the current is 3 miles per hour. The trip upstream takes 5 hours and the return trip takes 2.5 hours. What is the speed of the motorboat? A uniform motion problem can also be organized using a table. And generally speaking, our row headers can be labeled with trip 1 and trip 2, although we will be more specific with our row headers in just a moment. And again, we're going to label our columns with two quantities that can be multiplied together to give us the product, which we'll put in the third column. Let's recall that distance is equal to rate times time, and so our column headers are going to be rate multiplied by time, which is going to give us the distance. Let's look at a concept drawing to get some help populating the cells in our table. Here we have a boat that's traveling up a river and then back again. So instead of labeling our rows with trip 1 and trip 2, let's be a little more specific and call our rows upstream, and then the return trip we'll call downstream. Let's say the current of the river is moving in this direction. If our boat is traveling against the current, that means we're moving upstream. If our boat is traveling in the same direction as the current, that means we're moving downstream. Let's look back into the problem to see if we're ready to start populating some of the cells in our table. Rereading the question, it says, a boat heads upstream on the river where the speed of the current is 3 miles an hour. Since we're being told the speed of the current, let's go ahead and label that quantity in our concept drawing. The trip upstream takes 5 hours, so we actually can go ahead and put 5 in our time column. And the return trip takes 2.5 hours, so the trip downstream is going to take 2.5 hours. We're being asked to find the speed of the motorboat. So that is our unknown quantity. What is the speed of the motorboat? Let's also indicate that unknown down here in our concept drawing, making sure to identify that x is equal to the speed of the boat. Before we go any farther, let's discuss what it means to maintain a speed relative to the water. Two common phrases that you'll see in uniform motion problems are speed relative to the water and speed relative to the ground. Speed relative to the water is basically referring to the speed of the boat if there were no current pushing the boat one way or the other. Essentially, it's how fast the boat moves over the surface of the water when the water isn't moving itself. I like to think about this as the speedometer reading. If you're in a motorboat and the speedometer reads 9 miles an hour, that's essentially how quickly the boat is moving over the surface of the water, but not necessarily how many miles we're covering over the ground. The speed relative to the ground is the true speed of the boat. You might also see this referred to as the ground speed. The ground speed refers to how much distance we actually travel in 1 hour. So if our speed relative to the water was 9 miles an hour, but we were also being pushed forward by the current, we might actually cover 15 miles in 1 hour. So in this illustration, we would say that the ground speed is 15 miles an hour, even though the speed relative to the water was only 9 miles per hour. This represents the distance that we actually traveled in that 1 hour, of course greater than the boat speed because of the fact that we were assisted by the current. So back up here in our example, when we're discussing the rate in the rate column, what we're after here is actually the ground speed, which represents the true rate that the boat was actually traveling, having been assisted or hindered by the current. When traveling upstream, we're traveling against the current, so this is going to be slower. When we travel downstream, we're traveling with the current, and so this is going to be faster. So our upstream rate is going to take into consideration the speedometer reading, or basically the speed of the boat, and we're going to, from that, subtract the speed of the current to get the actual speed that we were traveling upstream. So this would be the boat speed minus the speed of the current as our true speed. When traveling downstream, we have our boat speed being assisted by the current. So we take boat speed and we add 3 to that. Now, as with previous examples, once we have 2 columns populated, we can multiply these 2 columns together and put their product in the third column. So our third column becomes 5 times x minus 3 and 2.5 times x plus 3, which is essentially our rate times the time, which is giving me the distance. Now it's time to set up our equation. And what we know about the trip upstream and the trip downstream is that they're going to be the same distance. We travel some distance upstream, then we turn around and we come the exact same distance back. So let's say that the distance upstream is going to be the same as the distance downstream. Our distance upstream was 5 times x minus 3, and that has to be equal to the distance that we traveled downstream, which was 2.5 times x plus 3. Now we're ready to solve this linear equation. So we'll distribute the 5 into the parentheses on the left to get 5x minus 15, and distribute the 2.5 into the right-hand side to get 2.5x plus 7.5. We get our variable terms to one side of the equation, which leaves us with negative 15 on the left, negative 2.5x plus 7.5 on the right, and then we subtract 7.5 from both sides to get negative 22.5 on the left and negative 2.5x on the right. Now we divide by negative 2.5 to completely isolate our x, and we get negative 22.5 divided by negative 2.5 is 9. And since x represented the speed of the boat, our units are going to be in miles per hour, and so this is our final answer.